The weighted residual formulation. This should seem familiar to you because the weighted residual method is already introduced to you from your bachelor study. Of course, I understand that a lot of you are online students and you might have studied some years ago and it may be difficult to recall everything. So there'll be a short recap. But if you also look at the videos of the fundamentals or also go back to some techniques in numerical analysis, you will find a good amount of information on the weighted residual approach. Now, you are only going to use certain limited type of weighted formulation, which is called the Galerkin method. So it's good to know that there are other methods that exist, but it's not absolutely necessary for you to be aware of all other techniques, especially not for this course. Of course, it's very important that you know it for your information and for other courses or for study or for doing mathematical manipulations. But for this course, whatever I teach you in this lecture is enough. Now, the weighted residual formulation, generally, if you look up, will be 4 or 5 different kinds of methods. As I already said, we will only use the Galerkin method. Now, to give you a flavor, a short, very brief one of what weighted residuals actually mean, is we'll just start with definition of the residual first. So let's consider that we just still look at the same problem that we have been looking at. We have a certain block of material which is under a certain load. Let's call this F, and of course it's always fixed on one side because that's the example I like to use. This is not varying in cross section, it's just uniform cross section, just using a representative volume. And it has certain material properties and cross sectional area, all that is given. We know those kind of things, so I'm not going to dwell on that. And of course it's moving, the load is applied along direction x, and this is at x is equal to 0, it's fixed, right? So we know that any physical system, let's just forget about this example for a minute, but concentrate on any physical system. Any physical system that's around you can be defined mathematically by means of a differential equation. We already know that. So you have a certain state of this system, right? So if we just go back in time to very young days and we studied about equilibrium, then we did a very simple example where there was a flat surface, and on this flat surface there was a very heavy bottom object, and then we applied a certain tilt to it, and then it would just basically rotate or pendulum wise move and then come back to equilibrium position, which was almost always like this. So this was its equilibrium position, always coming back to its own position. But there were also situations where you actually had, when you threw over something, so if you had an object which looked somewhat like this, and then you applied a certain tilt to it, it would just basically fall on its side and it would take somewhat of a shape, something like this. Sorry about bad drawing, but you get the picture. So it basically tips over on one side, and that becomes its equilibrium state. So what's happened is that we have changed its state of deformation or state of displacement, state of location. And all mathematical problems, if you look at them, they're always looking for equilibrium. So the only way we can find equilibrium in these cases is actually to find out what is the final state of rest or state of equilibrium or state of stability for this kind of a structure or any kind of a structure. So now if you get the drift of that, you probably understand that it's very important to know the state of deformation. So if we come back to the example that we have been dealing with so far, we see that there is a certain force that is applied, and we know that under this force there will be a certain deformation state under which this part will be in equilibrium. And everything that is being done in finite element method or in solving a differential equation is actually to find out this state of deformation. So basically we want to find out what is this delta L, right? So that's the basic crux of finding a residual. Now how do we link this to residual? If we have a certain condition, let's pick this one. We can write it in the form of a differential equation, which is described as AE du dx minus P is equal to 0, with boundary conditions with when x is equal to 0, u is equal to 0. So this is the boundary condition and this is my differential. that defines the problem. Now, the idea is that I have to find out the u that satisfies this problem. So I can have an assumed approximation of u. So I can say, yeah, I guess that there is a certain state, u is equal to blah, 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 where this equation will be satisfied. So I will put it in the equation and I will find a certain solution and I will hope that it comes to being equal to 0. But when I have an assumed approximate solution, it's not exact, I will most definitely not get a 0. So in place, I will always get a certain value which I can call as a residual. You can also look at residual as some kind of an error. And all problems that we are dealing with is basically to make the error or the residual go down to 0. So if we reduce the error or reduce the residual, we get the right solution. Now, by assumed approximation of u, we can't just pick an arbitrary u, right? So we have to be careful about what choice we make about u. So the assumed approximate solution has to satisfy certain conditions. It has to, let's say the conditions are, it has to satisfy the initial conditions of the problem. It has to satisfy the boundary conditions of the problem, and it has to be continuous. It has to be a continuous function. So if all these categories are met, then it's a viable assumed approximate solution, because if you put garbage in, you will get garbage out. So you also have to make sure that you pick the right sort of the correct displacement function direction and not just anything that you fancy, right? It has to be suitable to the problem you're looking at. So once these conditions are met, you'll be able to put it in, get the residual. So let's just pick an example because it's much easier to study with example. Let's just say that we take a polynomial function for u for the given problem that we've picked up with the differential equation known to us. So we can say that the assumed approximate solution function u is a function of x, of course, because it's in the direction of x, and we can say we go up to the third order polynomial. So we just say x squared, x cubed, and it always has to satisfy all these three conditions. So if you check carefully, all the conditions are going to be satisfied. Now my job here is to find out the values of C1, C2, C3 so that I can get the exact solution to the problem. So I'm going to start, as I mentioned, with the weighted residual formulation. So I have a u, I'm going to substitute it into the differential equation. And to substitute into the differential equation, I will have to write it as du dx, which is very simple. C1 plus 2c2x plus 3c3x square. Substituting this back into the differential equation, I can write it as AE c1 plus 2c2x plus 3c3x square minus p. And this will be equal to now the residual r because it's not equal to 0. So that is the formulation of the residual. In the lecture notes, I use slightly different notations. I can use small r instead of capital R and so on. But I'm sure you will forgive me for that and look beyond that. Now this is just the formulation of the residual. Now in the weighted residual formulation, there are a number of different methods, as I already explained. But we are only going to look at one particular method, which is called the Galerkin method. In the Galerkin method, you have to minimize the residual to get a solution to the given problem by forcing a certain condition, which is that we have to pick up weighting functions which have to be orthogonal to the residual. And the number of weighting functions will always be equal to the number of unknown coefficients that you want to find out. So you can always get the same number of system of equations to solve for the unknown number of coefficients. So by the Galerkin formulation, we enforce that if there is an integral of limits a to b over the residual r which goes over a certain length dx, then it has to be orthogonal to certain weighting functions wi, where I can have a certain number n, which is basically equal to the number of unknown coefficients. So if we continue with the same example that we've been working with, let's just pick some weighting function. So we say weighting function have to be 3, of course, because we have 3 unknowns. So we pick w1 as x, w2 as x squared, and w3 as x cubed. You could also pick sine x, cos x, etc. Yeah, that's also possible, as long as it satisfies, it can be fit in and satisfies the conditions. So you can have, it depends on the weighting functions now. So you can pick up some problems, basic problems from these textbooks, and you can see how to solve these problems quite easily. Generally, the weighting function is provided to you in these problems because you're not developing something new. This is already known to us. Yeah. So you can just basically substitute now everything back into the integral. So we know for our problem that it was for a given length of the element L. There's a force F acting here, or let's just call it P, it's easy. And this is fixed then. And we can just write now everything in terms of the integral. So the integral will be from 0 to L because it's over the length. Then we have the weighting function. The first weighting function is x. The residual we already calculated in the previous one, in the previous slide. So if you don't remember, you can have a look again, just slide back, or I'm sure you're making notes alongside. Now, what you need to do here is that you have to fill up the same 3 times, right? One with W1, once with W2, and once with W3. When you solve these system of equations, you will end up with 3 sets of equations, which is corresponding to 3 unknowns. When you solve them, you will get the value of C1, C2, and C3, which will lead to the exact value of U that you have been looking for. So that's the system of the Galerkin, right? So just as a recap, we know that there is a certain system which is under certain kind of loading. When it can be described mathematically using a differential equation, we can find out the state of stability. And for that, we have to assume a certain approximate solution for its displacement state. The displacement state must, the assumed displacement state must satisfy the initial conditions, the boundary conditions, and has to be continuous because we need some manipulations done on it. Then we substitute it back into the differential equation, and whatever error we get by substituting it back is called as the residual. Now our job in the Galerkin method is basically to reduce this residual by enforcing a certain condition that it has to be orthogonal to a certain weighting function, and these weighting functions have to be equal to the number of unknown coefficients. You enforce this integral over it and you find out 3 sets of equations which satisfy these conditions, and you will be able to solve this to get the 3 unknowns. Now, this is all very good. I'm not going to solve a problem with this. I'm not putting numbers to it, but you can do the exact same problem we did before, and you will also find it in the lecture notes. You'll be able to replicate the results to see that you can actually quite easily get the exact solution of U by using this method. But we need to focus on the finite element formulation, and how exactly are we going to do that? With the Galerkin method, it's absolutely important that the weighting functions used in the finite element formulation is the same as the characteristic of an element, which is termed as a shape function. Now, since we have not introduced you to the shape functions, I would first like you to do that to understand what shape functions are, and then we will get back to setting up a finite element system of equations with the Galerkin method. Okay, so follow the video first on the shape function formulation and come back to the Galerkin formulation.